Let's look at the next very important chapter, which is playing with numbers. Now it might, from the title itself, it might not be evident what this is all about, but the chapter deals with factors and multiples and related very important number theory concepts. So here are, as usual, some questions. We'll start with a few questions. If you can give answers to these questions, then you are all set. You can probably go through this chapter very fast and attempt the questions given here in this video as well as in the book itself. So without practice, of course, there is no gains. Okay, so definitely maths means practice. So you have to practice, no matter whether you already know these concepts or you are now listening to this video and understanding the concepts. Definitely do practice. In the resources below also, we have listed several links where you'll be able to practice the questions on these very important concepts. So the very first topic, of course, is factors. What are the factors themselves? Then we'll move on to the next important topic, which is fundamental theorem of arithmetic. Then we'll discuss the multiples and what are their properties. Then some esoteric things like common factors, common multiples, coprime numbers. What do those mean? Then the next very important topic, from which problems are definitely asked, which is the HCF, LCM and the word problems based on that. So students have some trouble translating from these word problems to actual mathematics, and we'll look at those in some details. Then we'll move on to prime and composite numbers. Of course, the sieve and the special prime numbers. Aristosthenes' sieve is of course very interesting, and we'll go through that in some detail. Finally, we'll move on to the divisibility test of the numbers and see how we can simplify our maths by using those divisibility tests. So very exciting topics, very important. Let's just quickly start. So to get an insight into what factors really are, let's use help from other subjects. So here we have number of living beings, and here we have a rock. So as we studied in other subjects, these living beings, they can be broken down, or they are made up of what we call cells. Similarly, all matter around us is made up of things called atoms and molecules. So in the same way, the same analogy can be used on numbers. So for example, can we break this number 6 into smaller constituents? See, one of the ways in which this can be done is by using the function of addition. So this we have already studied. We can write 6 as in terms of 2 and 4 by using addition. So in essence, I have broken down 6 into its two constituent terms, and those two terms are joined by addition. Similarly, I can write 6 as 5 plus 1. I can also write 6 as 6 plus 0. I mean, this is somewhat degenerate because 6 appears on both sides, and this can continue forever. In terms of addition, I can always express a number as 1 plus 1 plus 1, right? So I can always break down into a number of ones joined together by addition. Can we do it using multiplication? Yes, of course. And this is the basis for this entire study of factors. Breaking down a number in terms of multiplication of other numbers or other positive integers. So here I have broken down 6 into two of its constituents essentially. Each of those constituents is known as a factor. So these 2 and 3 are factors of 6, and when I multiply these two factors, 2 into 3, I get back the number 6. On the other hand, 6 is said to be a multiple of both 2 and 3. So 6 comes in the table of both 2 as well as 3. That's what the multiple means. Similarly, I can also write 6 as 6 into 1. Of course, this is again like we said, this is somewhat degenerate because this can go on forever. So I can write 6 into 1 is equal to 6 and then break down this 6 again into 6 into 1. But nonetheless, this is also a very valid factorization, right? Breaking down a number into its constituent factors. This is also valid factorization of 6, where both 6 and 1 are also the factors of 6. So a number itself and 1 is always a factor of a given number. Now let's try to visualize these factors and see what it actually means. So here I have 6 balloons. You can see that I have arranged them into row and column. As we already said, the total number of balloons is equal to row into column. So this would be equal to 1 into 6. This fact is represented using what we call a factor tree. Factor tree is a visual aid, is an easy way to factorize a number. So here the number is 6. I am factorizing it into two of its constituents, 1 and 6. And of course, when I multiply the two constituents 1 and 6, I get back the number 6. So this is the diagram of arrangement of row into column, and here we have the corresponding factor tree. This factor tree is used to break down a number into its constituent factors. So this is what we would be studying in great detail. Here is another way to factorize the number 6. We already looked at this. I can write number 6 as 2 into 3. We already looked at it, and this is the corresponding diagram, row into column, and number of columns in this case is just 3. Now this is another way. 6 is equal to 3 into 2. This is another valid way to factorize the given number. Again, this can be written as 3 into 2, which is equal to 3 rows and 2 columns. So here we have 3 rows and 2 columns. Of course, the final way to factorize the number 6 is in a single column, which means that I have 6 rows and just 1 column. And of course, when I multiply 6 and 1 together, I get back my number 6. So these are all the valid ways of factorizing the number 6. They are all equally valid. These two are actually equivalent. Why is that the case? Because we already know from the commutative property of multiplication, whether I do 2 into 3 or 3 into 2, I get one and the same answer. The answer would be 6. And these two methods, both this and this, give me the two factors of 6, which are 2 and 3. These two again are exactly equivalent. Here also I get the two factors of 6, which is 6 and 1. Okay, 6 and 1 are also valid factors of 6. That is something that we have to understand. However, there is a difference between these factors 6 and 1 and these factors 2 and 3. Number 2 and number 3 are special. And why are they special? They are special because I cannot break them down any further. Okay, so the only way to write number 2 is 2 into 1, and the only way to write number 3 is 3 into 1. So the only factorization of these two numbers 2 and 3 is the number itself multiplied by 1. That is it. We call such numbers prime numbers, and in this case we call them prime factors. So these are the prime factors of number 6. So these are actually very, very special. So if we say that factorize the number 6 in terms of its prime factors, we'll say it is 2 and 3. 6 is not a prime factor. Why is that the case? Because 6 can be broken down further into 2 and 3. Similarly, 1 is not the prime factor. Okay, 1 is not a prime number at all. It is not a prime factor. So although this is a valid factorization, 6 into 1 and 1 into 6, these are not prime factors of number 6. What are the prime factors of number 6? Prime factors of number 6 are 2 and 3, and we can write it as prime factorization, we can write it as 2 into 3. So that is something that we have understood. Now let us just take another example and see if we can come up with factors of another number. Let's say number 12. So again, we can break down the number 12 into several of its factors. So I can write it as 3, 4, 1, 12, 6, 2. So these are all the factors of number 12. Each of these factors of number 12 actually divide number 12. Out of all of these factors, 3 and 2 are the prime factors of number 12. Other factors 4, 12 and 6 can be broken down further, and therefore they are not the prime factors. So these are not the prime factors of number 12. Okay, so I hope this concept is now very clear. Another thing to understand in this case is, like we already said, in case of 6, 2 and 3 are actually factors of 6. On the other hand, 6 is a multiple. 6 is said to be the multiple of both number 2 and 3. What does that mean? It means that 6 would appear in tables of both 2 and 3, which we understand, right? Because when we say table of 2, it is 2 1s are 2, 2 2s are 4, 2 3s are 6 would appear. Again, in the case of 3, it would be 3 1s are 3, 3 2s are 6. So again 6 would appear. So 6 would appear in tables of both 2 and 3 and is said to be the multiple of both 2 and 3. Now let's take an example of 12 also. Can we list down some of its multiples? We can, right? So for 12, we can write down number of its multiple, which is just the table of 12. So it will be 12 and then 12 1s are 12, 12 2s are 24, 12 3s are 36. These are all multiples of 12. On the other hand, when we wrote the factors of 12, 12 is a multiple of each of its factors, right? So that is the relation. On one side we have factors, on the other side we have multiples. The multiple, like the number 12, is a multiple of all its factors. Now with that, let's look at the factor tree in some detail. So here we have taken a slightly larger number, and again we are trying to break down this number 24 into its constituent factors. So here we start with number 24, that is at the top. We call it the root of the factor tree. So in some sense, this tree, if you compare it to a real tree, it is inverted. So we start with the root at the top and we then go on to the leaves at the bottom. So this is the root and these are the leaves. In the middle, we list down factors of number 24. So the first thing we do is that we break down 24 into two of its factors, which is 6 and 4. So I can do that. I can write 24 as 6 into 4, which is a valid factorization of number 24. Then further down, I break down the number 6 into two of its constituent factors, which is 2 and 3. And I also break down the number 4 into two of its constituents, which is 2 into 2. There are again a few things to note here. The numbers, the factors which come in the middle right here are actually not prime factors. So both 6 and 4 are not prime factors of number 24. Why is that the case? Because they can both be broken down further. The numbers which come at the leaves, at the end of the tree, they are the prime factors. So what are the prime factors of number 24? If you were asked, you will draw this factor tree. You will start with the root and continue to break down until you get to numbers 2, 3, 2 and 2, and then you will say that the prime factorization or the prime factors of number 24 are 2, 3, 2 and 2. So that is the prime factorization. Another thing to note about this factor tree is that if I multiply all the numbers at a given level, so if I multiply them all together, the answer comes out to be the root of the tree. So I get back my number 24. Let's look at the next property of this factor tree. Okay, so these properties are very, very important. Here I have written down another prime factorization. Okay, so we saw the one prime factorization of number 24 right here. This is another prime factorization, another factorization, sorry, not prime factorization, but another factorization, another factor tree for number 24. And both of these trees, both of these factor trees for number 24 are equally valid. They are both correct. Each of the subtree, right? So for example, this is my main tree starting with number 24, and here I have a subtree starting from number 12 and going down. So each of those subtrees, let's just look at the tree of 12. Each of those subtrees are complete factor trees. So here this tree starting from 24 was a factor tree for number 24, and the subtree which started from 12 is a factor tree, is a complete factor tree, complete and valid factor tree for number 12. So that is the next property for the factor tree. The third important property of this factor tree, which we all understand by now, is that all the nodes, all these numbers which occur in the factor tree are actually factors of number 24, right? It's kind of understood, but that is the case. All these numbers 20, 12, 2, 4, 3, 2 and 2, they are all factors of number 24. Similarly, all the numbers which occur below number 12, right? So if I go below number 12, these are all the numbers which occur below number 12. They are factors of number 12. If I go below number 4, then all these numbers which occur below 4 are factors of number 4. Note one thing, okay, which we'll see in this case here, is that these factor trees, they do not list all the factors. So that is very important. You have to remember that. For example, this factor tree number 24, okay, so we saw all the factor trees of number 24. These are 3 ways of writing the factor tree of number 24. They are all valid. They are just different ways of doing the factorization of number 24. So the first thing is that the factor trees are not unique. I can just draw many factor trees for a number. So these are the 3 ways I wrote for 24. You can perhaps come up with other ways yourself. The second thing is that all the factors do not occur in a factor tree. So that is very important. For example, if you consider this factor tree, the very first one, this one, number 8 is missing here. The number 8 comes here. Number 12 is actually missing from both this and this. So factor tree does not list, it is not complete. It does not list all the factors of a given number. So one factor tree might list one factor, other factor tree might list other factors, right? So these are all the unique terms, terms unique to a factor tree, which are not found in other factor trees, and we have put the star next to them. The second and most important properties of these factor trees is that if you look at their leaf levels, if you look at the end levels, they will list all the prime factors of the root number, right? That is very important. So here with the star terms, we have listed the prime factors of root number 24, okay? And the prime factors for each case are exactly the same. No matter which factor tree you draw, they list all the prime factors of number 24. They are complete and they are the same across all the factor trees. So I can write 24 as 2 into 3 into 2 into 2 in terms of its prime factorization, and that I can get from any factor tree that is uniform across all the factor trees. So here we'll go like this, we'll list all the prime factors. Here we'll go like this and list all the prime factors, and similarly here we'll do the same. So that is very important. Okay, so the leaf nodes of any factor tree of number 24 would list all its prime factors. Let's summarize all the properties of the factor tree that we have studied so far. So the very first property is that if we multiply all the numbers at one level in a factor tree, I get back my original number. So it is very evident, self-evident in the first tree. If I multiply 6 and 4, I get back 24. If I multiply 2, 3, okay, so this, if I multiply these numbers together, 2, 3, 2 and 2, I get back my number 24 again. However, let's see why it is true in this case also, in this tree also. So in the very first level, it is very simple. It is very self-evident. If I multiply 12 and 2 together, I get back number 24. What about the next level? Clearly, if I multiply 4 and 3, I do not get back 24. So there is something wrong here. To really multiply all the numbers at one level, we have to extend this number 2 also to the next level. And of course, I can do it by extending 1 and writing it as 1 product of 1 and 2. And then my property actually becomes true. So then if I multiply 4 and 3 and then multiply it by 2, 4 is a 12, 12 is a 24, I get back my number 24. Similarly, to go to this level, I would have to extend all my levels down below. So 3 also I will have to extend, so I will say 3, 1, and then this 2 also I will have to extend, and I will say 2, 1, and then I will have to multiply all of these numbers together to get back number 24. So this property is definitely true. However, to make it true for each and every tree, we have to create it like this. We have to bring all the levels down. That is necessary. The second important property of factor tree is that it is not unique. I can create several factor tree to represent the factorization of a number. So that is definitely we have seen. Another important property that we have seen is that a factor tree does not list all the factors. So for example, 6 is a factor here, but not in this one and this one, right? So we have seen that also. The next important property is that each of the subtree is complete factor tree in itself. So this is the factor tree of 6, this is the factor tree of 4, and of course this entire thing is the factor tree of 24. The very last and the most important property is that if I look at the leaf nodes of any factor tree, it gives me the prime factorization of number 24, and this prime factorization of number 24 is unique and same across all the factor trees. So this is the most important property. The next thing that we'll look at is the properties of factors themselves. So we have looked at the properties of factor tree. Now we'll look at the properties of factors of a number. So we have already seen that in case of the factorization of number 24, all of these 6, 4, 2, 3, 2 and 2, all of these are factors of number 24. There are other factors as well, like for example 8 is also a factor. It's not listed here, but it's there nonetheless. Similarly, for 6, one of the ways to factorize it is 1 and 6. So both 1 and 6 are actually factors of number 6. So here is the list of all the properties. 1 is a factor of every number. So in this case also we can write 24 as 24 into 1. So 1 is definitely a factor of 24, and we can show it in this factor tree as well. Okay, we chose not to show it, but it can be shown. Okay, so if I want to bring 1 as a factor tree for 24, I can extend this number 2 or number 3, any one of those numbers, and write it as 2 into 1. So in that case, 1 would become, it would come in the factor tree of 24 and become a factor of explicitly become a factor of 24. Okay, but it is, even if we don't list it, even if we chose not to draw this line, 1 is implicitly, it is given that it is a factor of number 24. Similarly, the number itself is always a factor. That is true. Okay, because number can always divide itself. So number is always a factor. The next important thing is every number, every factor of a number is a divisor of that number. What does that mean? It means that if I divide number 24, let's say I divide number 24 by any of its factors. If I divide it by 6, I get back a quotient. It is a perfect division. Okay, there is no remainder left. So this 6 would divide this 24 evenly, and I'll come up with number 4. Every factor, okay, not only 6, even 4, 2, 3, all of those numbers would divide the number 24 perfectly. A number itself, 24, would always divide the itself. The quotient would be 1. Similarly, 1 would always divide any of the numbers, right? So for example, if I divide 24 by 1, I get an even division, and my quotient in this case is 24 itself. The next important property is that all the factors, okay, for any number are either less or equal to the given number, which is kind of, it comes back from this property that we have already studied, because the factor has to divide the given number, either it has to be less or equal to the given number, right? So in this case, all the factors 6, 4, 2, 3, all of them are actually less than 24. Other factors like 8, 12, they are also less than 24. 24, it is a factor of number 24, but that is equal, right? So 24 is equal to 24. So that's why we have this less than and equal is very important, okay? Because this equal has to be there, because any number is a factor of itself. So this equal has to be there. The last and another important property is that I can always list down the factors of a given number, and we'll do that exercise in just a minute. We'll list down the factors of a number, but that is a property. It is finite. The number of factors of a given number, for example 24, are not infinite. I should be able to list them down. I should be able to calculate each and every one of those. So let's just do exactly that now. Let's just list down the factors of number 84. So here what we have done is that we have written down the prime factorization of number 84. So that I can do, it is very simple. Not prime factorization, I have drawn a factor tree. I have done the factorization of number 84, and I have come up with all the prime factors. As we said, or we have been saying, the prime factors always come out in the leaf. So these leaves are just the prime factors of number 84. So the first thing I do is that I list down the prime factors of number 84. So I can always list it out like this. Okay, so by convention we actually write it slightly differently. We always start from the smallest prime factor and then move on to the larger one. So this is just a convention. It also makes things a little easy for us. We'll see that in a second. To list down, so these are the prime factors. So we have come up with the prime factors. Now we have to come up with the factors of number 84. So how would we do that? See, prime factors are included in the factors. So they are definitely the factors of number 84. So that is the given. 1 is always the factor. So we'll start with 1 itself. Then we list down all the prime factors. So these are all the prime factors. They are also factors of 84. Then what we'll do is that we'll multiply 2 of these prime factors and come up with the other factors of number 84. So we'll take 2 at a time. We start with number 2 and we multiply it by 2. So I get 4. Then the other 2 numbers I chose are 2 and 3 and I get 6. Then I choose 3 and 7 and I get 21. Then I choose 7 and 2 and I get 14. So these are the factors of number 84 formed by multiplying 2 prime factors. So here we have multiplied 2 prime factors. Okay, so in the bracket I'll write 2. Okay, then we write down the factors of number 84 formed by multiplying 3 of these prime factors. Okay, so the first I choose 2 and 3, sorry. So this comes out to be 12. That is the first factor formed by multiplying 3 prime factors. Then we multiply 2, 3 and 7 and we get 7 3s are 21, 21 2s are 42. That's another one. Then we choose numbers 7, 2 and 2. Okay, so we'll just, this is 7, 2 and 2. And in that case we get 7 2s are 14, 14 2s are 28. So then we write down 28 as the next factor. Okay, so all of these factors are formed by multiplying 3 prime factors. So we write down 3 in the brackets. And of course we have already seen that number 84 is always the factor of itself. So we'll write down number 84 directly here. Okay, and of course number 84 is also formed by multiplying all the 4 prime factors together. So here we'll write 4 and we'll end. Okay, because at this point we have reached the number itself and we end at this point. And in this way we can systematically list down all the factors of a given number. So we start by prime factors, then we combine 2 prime factors, then we combine 3 prime factors, then we combine all the prime factors in case of 84. If there were more prime factors, we'll of course have to do little more work, but systematically we can list down all the factors of a given number. And as we have seen, the number of factors is actually finite. Okay, so that was our last property, and here we have sort of proven it. It has to be finite because the number of ways in which I can combine the prime factors is actually finite, right? Now let's look at a very, very interesting properties of numbers which are perfect numbers. So I'm very, very interested in such properties of numbers, such properties in number theory, and this property is related to the factors. So let's just look at it, and definitely it will develop your interest in factors, prime factors and factorization, I guarantee. So for certain numbers, interestingly, if I add together all their factors, right? So I write down all the factors of the number, and if I add them together, that sum is equal to twice the number, right? Interestingly, and it is not true for one number, it is true for several numbers. So here is an example. Let's just write down, see with the help of an example. So let's just do prime factorization, or not, sorry, not prime, but let's just list down all the factors of number 28. So of course we start with number 1 and we systematically are writing down all the factors of number 28. Okay, and of course 28 itself would come in this case. See, another thing that I have done here is that this fact 28, the number 2 appears actually twice, but I have just written it down once because I am only taking the unique factors. So I am taking only the unique factors. I am taking 2 only once. So if you are listing down the prime factors of 28, the 2 would come twice. Okay, it is 1, 2, 2 and 7. Okay, it's not 1 would not be there. It is not there in prime factorization. In prime factorization of number 28, it would appear as 2, 2 and 7, but we have taken only 2, 1, 2. Okay, we have not taken the other 2. So we keep 2 only once. That is what this unique actually means. Now if I sum all of these factors, it comes out to be equal to 56. And this 56 is 2 times 28. Right? Very, very important. And for numbers in which such property, which this property holds, are known as perfect numbers. Now you would think that it is very, very interesting. Why would we be interested in perfect numbers at all? Again, we go back to ancient Greeks, where in the science, not really in the science, but in astrology, they were using this concept of perfect numbers to see that some of numbers are auspicious for certain things, other numbers were auspicious for other things. Similar to the concept of perfect numbers, we had the concept of deficient numbers as well. Deficient number is one where the sum of unique factors is less than twice the number. So here let's take an example of deficient number as well. We take down the example of 14. So 14, again I list down all the unique factors. Okay, we are listing only the unique factor, which means that if a factor is appearing twice, we only take it once. That's what unique factor actually means. So I am listing down all the factors of 14, and it's relatively simple. 14 itself, and then of course we will end there. And if I total this total comes out to be 24. And this total 24 is less than 2 times 14. 2 times 14 is 28. So this 24 is less than 28, and therefore 14 is a deficient number. So 28 we saw was a perfect number. 14 is a deficient number. The next and the final kind of numbers are abundant numbers. And what does that mean? It means that the sum of unique factors, so I take all the unique factors, the sum is greater than 2 times the number. So those are the abundant numbers. And again, as you can see, these perfect numbers, deficient number and abundant numbers, they are important not mathematically but astrologically. For certain things, they found that deficient number were important, they were more auspicious, so they will try to use that number in those ceremonies. For other things, they saw that abundant numbers were more auspicious, so they will try to use abundant numbers for those ceremonies. And of course, perfect numbers were reserved for very, very special ceremonies, and they would try to use those many things in their ceremonies itself. Let's take an example of abundant number, which is our favorite, one of the favorite numbers, which is number 12. Again, we list down all its factors. See, again in case of number 12, if I write down the prime factorization, it would come out to be 2, 2, 3. But here we are listing only the unique factors. So from these two 2's, I'll just pick 1, 2 and I'll put it here. From these 3, of course, there is 1, 3. So we'll just put it there, and then 6 would come, and then 12 itself would come. I missed one factor, which is 2 into 2, 4. Okay, so 4 is also a factor, and we'll list it down right here in the middle. So if I make a total of all of these factors, this again comes out to be 28. Now this total of all the factors is 28, which is of course greater than 2 times 12. 2 times 12 is 24. Okay, so this 28 is greater than 24, and therefore we say that this number 12 is actually an abundant number. Again, very, very interesting topic. Now, as we have already seen the prime factors of a number, right? So we did the prime factorization of, for example, number 24, and we created various factor trees for it. So for 24, we were able to create these 3 factor trees. But one of the things that we actually noticed was that the prime factors, the leaf nodes of this, all of these factor trees are always the same. So no matter what factor tree we draw, what path we follow, we end up having these 4 prime factors in all of these cases. So 24, when we are dividing into its prime factors, we always get only these 4 numbers as answer. See, the order of these terms is not really important. By commutativity and associativity of multiplication, if I change the order, I am not changing anything, okay, in case of multiplication. But only the terms are important. So no matter how I divide 24 into its prime factors, I only get these 4 prime factors. And this is our fundamental theorem of arithmetic, which states that every integer which is greater than 1 either is a prime number itself, so either that number would itself be a prime number, or it could be factorized into the prime numbers, into product of prime numbers, but that factorization would be unique. There is only one factorization of a number into its prime factors. There is only one such factorization. So for example, if we take number 36, I can factorize it as into its prime factors only in this way. So this is these are the only prime factors. They are kind of a signature. Only 36 would have 2 2s and 2 3s as its prime factors. If I change the prime factors, my number would change. On the other side, if we say 36 would have only these prime factors, and these prime factors would only be there for 36. So the rule goes both ways, and that is what this fundamental theorem of arithmetic is actually stating. Now there are few things to note here. First thing is that we are saying that the number is uniquely divided into its prime factors. Only the prime factorization is actually unique. For example, if I were to divide 36 into not prime factors, okay, but in composite factors, for example, if I do 12 into 3, then this thing is actually not unique. Okay, so I can do it as 12 into 3, or I can do it as 4 into 9. So this factorization in composite terms is not unique. Only the factorization, if I do factorization of 36 in prime factors, that is unique. That is the first thing to note here. Second thing is that 1 is not a prime number, which is good, because if 1 were a prime number, then this rule would not hold true. Why? Because I can always write, let's say 6. The prime factorization of 6 is 2 into 3. Now if 1 were also a prime number, then we could write 2 into 3 into 1. Or we could have written 2 into 3 into 1 into 1. But fortunately for us, 1 is not a prime number, and therefore this fundamental theorem of arithmetic actually holds true. So it is important for this fundamental theorem of arithmetic that 1 not be considered a prime number at all, and indeed it is not. Okay, so 6 again has one unique prime factorization, and that is 2 into 3. No other number in this world can have the same prime factorization as 6, and only 6 can only be done, the prime factorization, only in one way. Okay, so very, very important fundamental theorem of arithmetic. You should do this by heart, okay, and keep it with you. It will be useful forever in number theory. Let's now look at multiples and their properties. So we already know about factors at this point, and now let's consider about multiples. What are multiples? Multiples are very, very simple. In fact, they are so simple that you have already encountered them. Whenever you practice tables, everything which occurs in table of 12, for example, is a multiple of 12. Anything which appears in table of 9 is a multiple of 9. So I start with 12 ones are 12. So this is ones are, then 12 twos are 24, and I keep on writing the final answer, the final product. 12 threes are 36, and all of these final products are called the multiple of 12, including 12 itself. So 12 itself would also be included, because that is 12 multiplied by 1. Key thing here to note is that 12 would divide all its multiples. Got it, right? Same thing with 9. We start with 9 ones are 9, 9 twos are 18, 9 threes are 27, and we can go on forever. So these multiples, I can write as many multiples as possible. Each time I multiply the number with an ever larger number, I would get ever larger multiples. So this series would never end. The series of multiples never ends. That's the first thing to note. Second thing is that the number is always a multiple of itself. Now let's look at some of the properties of these multiples in terms of factor tree. So we have already looked at the factor tree. When we go down, we know that we always find the factors of a number. If we go up the tree, we always find the multiples of the number. They are not all the multiples, but definitely if the number is above another number in a factor tree, it is a multiple. Okay? It is not that if I go up 2, I will find all the multiples of 2. That is not the case. But if I am going up, definitely the number where I'll end up, would definitely be a multiple of 2. So from here we have the relation. This is the root. Root has children, and then grandchildren. Similarly, from bottom we have the relationship of parent and grandparent, and so on and so forth. So if we go up, we'll find all the multiples. Okay, so not only 6 but also 24 would be a multiple of this 2 and 3. Again, not all the multiples of 2 would be found in this tree, but if the number is found above a number in the factor tree, it would be a multiple. Now, with that, let's look at some of the properties of these multiples. So properties of multiples are actually important. The very first property is that all the multiples of a number either is equal to that number or greater than that number, which we understand, right? Because all of these numbers, the multiples are found by multiplying the number 12 with another number. So obviously they have to be greater than the number itself. Of course, the very first number 12 is multiplied by 12 into 1. Okay, so that would be the number itself. So for that we bring in the equal to sign. Okay, so take into account the very first case, 12 into 1, we bring in the equal to sign. The second property is that I can come up with as many multiples of a number as I possibly can, right? It's just up to my patience or my ability to do multiplication. But the number of multiples of a given number is actually infinite. The third property we already looked at, every number is a multiple of itself. So 12 would be a multiple of 12, 9 would be a multiple of 9, and that is to some extent understood. Now let's look at some miscellaneous terminology, which is very, very important, mind you. The common factors, common multiples, and Coprime numbers. So what do we mean by that? So first we start with common factors. So here I have shown the prime factorization of two numbers, 84 and 24. So very, very simple, not difficult at all. The prime factorization is, or the factorization of these two numbers, if you notice the factor tree, some numbers appear in both factor tree of 84 as well as 24. They are known as common factors. So 6 is an example. If we focus on the prime factors, then 2, 3 and 2, they appear in both the factor trees. And of course, they are also the common factors of both 84 and 24. So common factors, very, very simple, not difficult thing at all. Now let's just focus on the prime factorization of these numbers, 84 and 24. So the way I can do it is 84, the prime factorization would go as into 2 into 7. So it is the prime factorization. I have simply copied these numbers from the leaf of this tree. It's very, very simple, nothing difficult so far. Actually, the concepts are very, very simple. 2 and then 2 into 2. So that is what I have done. Now if I multiply these three terms together, what can I do? I can write them together as 3 to the 4 to the 12 into 7. Similarly, I can write this thing as 12 into 2. One of the things that we'll notice, the way I have come up with this number 12 is that I have taken the common factors, the common prime factors between these two numbers. I have taken them apart and then I have multiplied them together. This number 12 is very important because it appears in factors as factors of both 84 as well as 24. Not only that, it is the highest common factor, means that I cannot come up with a factor bigger than 12 which would divide both numbers 84 and 24. It is impossible to do that because all the common factors between 84 and 24, which is 2, 3 and 2, is incorporated into this number 12. So this number 12 is the highest common factor, is known as the highest common factor of these two numbers. At the same time, since this number 12 is the largest number which would evenly divide both 84 and 24, this number 12 is also known as greatest common divisor or GCD. Two very, very important terms, highest common factor and greatest common divisor. They mean one and the same thing, and now you understand the meaning behind these two terms. Another thing to note here is that although the words highest common factor have the word highest and the greatest common divisor has the word greatest, always the HCF and GCD are less than the numbers themselves. So my number 12 is less than 84 and my number 12 is also less than 24. So do not get confused by this terminology. although we call them highest common factor, because they are the factors, they have to be less than the numbers themselves. So very simple term. Now, of course, this 12 is known as HCF. We understand that. Very important. Let's now move on to the next important concept. Again, very important. Coprime numbers. So what does that mean? It means that if two numbers, let's say 9, 4, if I come up with the prime factorization of those numbers, that's what I have done here, I would not find any common prime factors between these two numbers. If that is the case, then those two numbers 9 and 4 are known as coprime. See, the key thing here is that neither 9 or 4 is actually prime. 4 is not prime, it is divisible by 2. 9 is also not prime, it is divisible by 3. But when considered together, we can say that 9 is coprime. Okay, so coprime is the relationship. Okay, so coprime is actually the relationship between these two numbers. I cannot say that 9 is coprime. No. It is not, does not apply to the number itself, one number. But coprime denotes the relationship between two numbers or three numbers, saying that they have no common factors between them except one. Okay. Using the same terminology, using the same sort of understanding, we can conclude that all prime numbers, for example 3 and 2, they are coprime. They are naturally coprime because between these numbers 3 and 2, I cannot find any common factor except 1. So 3 and 2, all the prime numbers are coprimes, but other than the prime numbers, I can still have coprime numbers. So here we have an example of three numbers, 9, 4 and 35. They have no common factors between them, and therefore, except one of course, and therefore they are all coprime to each other. So coprime, remember, it denotes relationship between numbers. It does not apply to an individual number. So very important. Now let's look at the next very important concept, which is common multiples. So multiples, as we already know, we can write them down very simply. They are the numbers as they appear in the table of other numbers. So for example, to write the multiple of 12, I simply replicate the table of 12. So it will go as 12 ones are 12, 12 twos are 24, 12 threes are 36, and so on. Similarly, to write down the multiple of 9, all I have to do is I have to just replicate the table of 9. 9 ones are 9, 9 twos are 18, so on and so forth. Very simple. So concept of multiple itself is very simple. To get to the common multiples, all I have to do is to notice that when I look at the multiples of 12 and the multiples of 9, certain multiples, they appear in both as both multiples of 12 as well as 9. So certain numbers would appear in both, and these numbers are known as the common multiples. The first such number in case of 12 and 9 is 36. So I write that down. The next number, of course, is 72, and after that 108. Of course, the common multiples do not really end there, and I can come up with infinite such common multiples between 12 and 9. The important thing to note is the very first multiple common between 12 and 9 is 36, and that is known as least common multiple because it is the least common multiple. very simple, between 12 and 9. Other multiples are simply the tables of this least common multiple, which means that other common multiples between 12 and 9 are just multiples of 36. So for example, 72 is 36 into 2, 108 is 36 into 3, so on and so forth. The next important thing to note or to really understand here, of course, we already saw that 36 is just known as LCM, or the least common multiple. Another thing which I want to bring across, the point I want to bring across, is to understand why this works. Why do we have the common multiples where we have them? So let's look at the factorization of 12. Let's just factorize 12 as 4 into 3. I can do that. There is no problem in that. 9 I can factorize it 3 into 3. If you notice, the factor which is missing from 12 but which is present in 9 is 3. So I bring it here. The factor which is present in 12 but which is missing in 9, I bring it here, okay, and if I multiply this number, this comes out to be 36, and of course this number comes out to be 36. Now how do we produce these missing factors? So produce the missing factor in case of 9, what do? We take 4 jumps of 9. So 4 was the missing factor, and if we take 4 jumps of 9, I have produced that missing factor in case of 9. So every 4th jump I would get a factor which is common to 12 as well in case of 9. Similarly, to produce this number 3, how do I do that? I take 3 jumps in case of 12, and every 3rd jump, 1, 2 and 3, I would come across a multiple of 12 which is common to 9 as well. Very simple concept. Let's now look at problems involving HCF and LCM, especially word problems. You can expect such problems in your exam. So very important concept, and I encourage you to not only listen to this video but also solve problems at the same time. Okay, so we have already seen what HCF actually means. HCF is simply the highest common factor between numbers. So here we have a few numbers, and one of the ways to really find the HCF of these numbers is to list all the factors. So what I can do is that I can start like this. I can start with 126 and I can continue to list the factors of 126. So I can list down the prime factors. That is how we go about doing it. So we start with the prime factors and then we combine these prime factors in various ways. So then I can combine this and this, 2 and 3 and so on and so forth. Then I can come up with rest of the factors of 126. Similarly, for 252 also I can do the same thing. I can start with the prime factors and then I can combine these prime factors again in various ways. Okay, so that is simple. We already seen how to do this. Then next number is 315, and for that I'll repeat the same exercise. First, let me list the prime factors and then I will combine these prime factors and come up with all the factors of these numbers. Once I come up with the factors of all these numbers, I'll find the highest factor among those which is common to all of these 3 numbers, and that would be my answer. So that is one way of doing it. Of course, it is very cumbersome, so we try to not do this method at all. Okay, so one of the methods which we can use if we are bent upon listing the factors, if you indeed want to use this method, one of the things that you can do is that look at all the prime factors for 126, 252 and 315 all together. See which factors are actually common. Okay, so we are looking only at prime factors. We are not considering the other factors at all. We are not going beyond prime factors. We are only listing out the prime factors and trying to find the common prime factors across all 3, mind you. Okay, so we have to make sure that we find the factors, prime factors, which are common in all 3 numbers. So we'll start. The very first one is actually 3. 3 appears here, here and here. So we make a note of that. Again, there is a second 3 which appears here, here and here, and so we make a note of that. My HCF is simply 3 into 3, which is 9, right? So that's kind of understandable. We have extracted all the common prime factors and multiplied them together, and of course that would give us the highest common factor. This would be the largest number which would divide all of these 3 numbers. Second method of doing the same thing, right? We are doing the same thing but sort of extracting the common prime factors. We are doing the same thing but in a little bit systematic manner. The way we do it is that we write down the numbers right here. I write down the number 3 which I know would divide this, this and this, and to find out if the number 3 would divide these numbers, we can use divisibility test, for example. Then I do exactly that. I list down 3 here and I divide 126 by 3. The answer is 42. Then I divide 252 by 3. Answer comes out to be 84, and for 315 the answer is 105. Okay. The next thing we do is that we see what is the next number. If there is any number which would divide all 3, at this point we need to find a number which would divide all three, not one of them, not two of them, all three of them. The number has to divide. For HCF, the number that we are writing here in this column has to divide all the numbers. Okay, so here now we list again 3, and we see that this 3 would divide all the numbers, and answer of course would be 14. 3 ones are 3, 8s are 24, and of course 3 3s are 9, 3 5s are 15. Okay, so that would be the, and after this point I cannot find any other number which would divide all three numbers. Okay, notice that 2 can divide these two numbers, but it would not divide this number, so we don't consider 2 at all. I have to write down number here which would divide all three. Okay, if there were 4, then that number has to divide all 4 of these numbers. So now I simply multiply these are my common factors, and I simply multiply this, and I say that my HCF is equal to 3 into 3, which is equal to 9. So either method is fine. Listing down the common factors, all the factors, and then finding the highest is not a good method. You can use either this method from 5 factors, or you can use this method. This method is the most preferable. It is the most systematic way of finding the HCF. Now let's move on. Okay, so this method, this is the summary of what we have done. We have included factors common to all the numbers. Okay, so that is important. We have to find out, we have to include a factor only if it is common to all the numbers. Okay, and then we include it as many times it appears common, right? So for example, in this 3 into 3 was common. Okay, so 3 was 2 times, so we included it 2 times. It's not that we included 3 only once. If it's common 2 times, we include it 2 times. Right? So very simple, not difficult at all. Now that we understand how to calculate the HCF, we'll look at the word problems in a second. But first, let's look at the properties of HCF. HCF is a factor of all the numbers. So that is true, right? In the sense that we already know that by virtue of it being the highest common factor, it is a factor of all the numbers. It is just that it is the highest possible factor. HCF is also the greatest number which can divide all given numbers, right? So for in this example that we just took, 126, 252 and 315, the greatest number which can divide all of these 3 numbers is actually 9. I cannot find any number bigger than 9 which would divide all the 3 numbers. The next property is that HCF is always smaller than or equal to given numbers, right? So equal to is also important. For example, if I have to find HCF of 6 and 12, I have to find the highest common factor between them. I have to find the number which would divide both 6 and 12, and at the same time it is the highest. The answer would be 6. So in this case, my HCF is just equal to one of the numbers. Okay, so 6 and 12, 12 happens to be a multiple of 6, and that is why this is happening. But in this case, my answer happens, the HCF happens to be one of the numbers. So that's why I have to bring in the equal to sign here. The next important and most important property is that if I take 2 Coprime numbers, for example 9 and 4, a very standard example, and I try to find out a HCF of these 2 numbers, that HCF would always be equal to 1. I cannot find any other number between these 2, and that is by definition. We already say that 2 numbers are coprime if there is not a common factor between them except 1. So 9 and 4 are coprime only because they have only one common factor, 1, and therefore the highest common factor would also be 1. So by definition this is true, but it is very important property. HCF is always equal to 1 for coprime numbers. You can expect Olympiad problems based on this fact. Okay, so in a subsequent class, when we'll be solving many more Olympiad problems, definitely we'll look at some of the problems based on this fact. Of course, by extension, this rule also applies to all the prime numbers, because all the prime numbers are coprime by definition. So with this, now let's look at word problems based on HCF. Again, very important concept. Word problems definitely would come in your exam. So when we are thinking about word problems based on HCF, the problems would always be of this form. Suppose I have 2 walls. Okay, I have 2 walls. One is, let's say, 18 centimeters long. The other one is 12 centimeters long. I want to find out the length of the largest possible scale, or the largest possible scale length which could measure both of these walls completely, right? Evenly divide both of these walls, which could evenly measure both of these walls. So what am I saying? Okay, so what am I saying? I'm saying that there is a scale, let's say 2 centimeters long. So I brought a scale which is 2 centimeters long. I can do that, and this 2 centimeter long scale would evenly measure, okay, complete lengths of scales would be covered. That's what I mean when I say evenly measure. This 12 centimeter long wall as well as the 18 centimeter long. Why is that the case? Because 2 divides both 12 and 18. Okay, so therefore only certain number of fixed numbers of scale, complete scales, would fit in 12 as well as in 18 if my scale length is 2. But the answer does not seek any scale length which could evenly measure these 2 walls. The question asks me the largest possible length. If I go with 3, again I would be able to divide both 12 and 18, but we are not looking for any number which could evenly divide 12 and 18. We are looking for the largest possible number which could evenly divide 12 and 18. What is that number? HCF, right? It is the highest common factor. So in such problems, when problem says that find the largest length, okay, find the highest number, those kind of problems where largest, highest, those terms come, we always have to use HCF. And HCF by its definition is a number which is the largest number which would evenly divide both 12 and 18. If I want to find out the HCF of 12 and 18, I can repeat the exercise below. That answer is 6. So 6 would be the length which would completely largest possible length which would completely measure, which would evenly sort of measure both these walls of 12 and 18 centimeter. If I go higher than that, let's say I try with 8 centimeters, I just tried, then this would not work, because this 8 centimeter I would not be able to measure 12, okay, the 12 would end at 4, and of course I would not be able to measure 18 as well, because this 8 does not divide any of those. So I am seeking the largest number, in this case 6, which evenly divides 12 and 18, both of them, and that number is simply my HCF. So in such problems, and the format of problem is structured like this, you are being asked highest number which would evenly divide 2 numbers in some form or the other, then use HCF. Highest, largest, those are the key terms. Okay, got it. Now let's look at a real problem. So here is one. See, we have length, breadth and height of a room. So there is a room, very simple. Okay, so we can create a room and we are being given its length, breadth and height. Not very difficult task. Okay, and I have to, again, problem is structured very similar to what we have just seen. So the length, breadth and height are given. It is these 3 numbers are there, and I have to find the length of the largest scale. In this case it's tape. Again, longest tape, largest scale, which would measure the three dimensions exactly. So which would evenly divide these 3 numbers, and of course we now know that is just the HCF. So very simple. Problem is not difficult at all if you look at the things carefully. If you are very careful, then these problems are very simple, very scoring, and computations fortunately are also not, the teachers, they give you simple computations, fortunately. Okay, so then what we do is that we simply start by dividing the numbers. So first we divide by 5. We know that all of these would be divisible by 5 by virtue of there being a 5 or 0 in the end. So again, using our divisibility test in our head, that's what we are doing, and the answer would be 165, and for this the answer would be 135, and for the last one the answer would be 90. Now from there on we again see that 5 would again be a factor of all of these, so we again divide by 5. Notice, like I said again and again, I am emphasizing, for HCF we continue this division only if all the numbers are divisible. Okay, if even one of the numbers is not divisible by, let's say it was not divisible by 5, I would stop right there. Okay, that is the key thing here. Do not, okay, in a second we'll look at LCM and there we'll do it a little differently. So keep this concept very clear, so that when we come to LCM you're not really confused. And of course at this point we can see that these numbers are all divisible by 3, and from there we will realize that at this point we will have to really stop. We cannot go any further. because this is 11, so we'll have to just stop. There is no number, these two don't have 11 as factors, so there is no number which can divide all of these three. So from here we know that our HCF, or the length of the largest step, is of course 5 into 5 into 3, which is equal to 75. So not very difficult at all, very simple, provided we are using our concepts. Our concepts are clear and we are applying them very carefully. Now let's move on to the other side of the facet and understand how we can calculate LCM. Again, we'll discuss two methods of calculating the LCM. We'll be considering these three numbers. And the first method is of course by prime factorization. What we do is that, as we did in the case of HCF, we write down the numbers in terms of their prime factors. So it is very simple. This becomes 237, and then for 105 the prime factors are of course 5, 3 and 7. Okay, so this prime factorization again is not very difficult. You can do it yourself. All the involved factors are very small. Okay, so you start by dividing the least number, and then for example you can start by 5 in this case, okay, because you know that 5 would be a factor, and then continue the process. The numbers would then become small, okay, once you do one division. So these are the prime factorization. We have done this for each of the numbers. Now in case of LCM, again the starting process is similar to HCF. We start by looking at the numbers, the factors which are common, the prime factors which are common to all three numbers. So the factor which is common to all three numbers is 7. So we simply write that down. Okay, so 7 would come in our LCM as well. Okay, that is the starting point. After that, so this was similar to what we did for HCF. We looked at the factor which was common across all three. After that, the similarity ends, and I want you to note this so that you are not confused. We then pick up the factor which is common to two numbers. So we pick up 5 as well. Okay, so we don't stop at 7 as we would in the case of HCF, but we move on to the next factor which is common across two numbers. Then 3 is also common across two numbers, so we'll take that as well. Okay, so this was common across all three. 5 and 3 were common across two numbers, and then finally we even take these 2 and this 7 are also taken, which have been left. Okay, so these 2 and 7 are present in only one of the numbers, but we even take these. So we don't leave out any of the factors. We are first taking the factor which is present in all three numbers just once. Then we take the factor which is present in any two numbers again just once. So we took 5 ones and 3 ones, and then we took the factors which have been left, which were there only in one of the numbers, and this would be our LCM. So that is the difference. Key difference is that we are continuing the process of taking the factors until we have extracted each and every factor of each number, right? So that is the thing to note here. For example, if you consider 42, all its factors are present here. 2, 3, 7 are all present here. Then if you consider 105, all its factors are also present. 5, 3, 7. So 5, 3 and 7 are present here. 245, 5, 7, 7. So 5, okay, 7 and another 7. Okay, so they are also present. So ultimately what would happen is that this LCM would be divisible by each of these numbers, which is correct only, right? Because that is a least common multiple. It is a multiple of all the three numbers. So it has to be divisible by these three numbers. And the process of choosing the prime factors actually ensures that. Okay, so that was the key thing here. Now let us look at the next method of doing the same LCM, and this is little bit systematic, and this is our preferred method. So we would use this method wherever possible. Again, we start by looking at the numbers and we write them in the tabular form. Then the first thing we do is that we see that the two of the numbers would of course be divisible by 5. So we start by dividing the numbers by 5. So 42 is not divisible, so it comes as is. Okay, so notice this is the difference again with the HCF. HCF, we would only choose a number here if it divided all three numbers. In LCM that is not the case. We would choose a number here which divides at least two numbers. So this 5 would divide at least 105 and 245. So we are using 5 here. Then we come on to 105. This becomes 21, and then 245, 49.
Then from here we know that all of these numbers are divisible by 7. So we write that down. So this becomes 6, this is 3, and this is 7 7s are 49. And from here again we would use another number which is 3, okay, because 3 would divide 6 as well as 3, so we choose 3, okay. So it divides at least 2 numbers, so that's why we are choosing 3. 3 2s are 6, 3 1s are 3, and 7 would come here. So our LCM would again come out to be 5 into 7 into 3, so we go like this, and then 2 and 7. Again, if you notice, these 2 and 7 are actually the factors which were completely left, which were not common to any of the numbers. So the process is very simple, if you proceed it systematically, then the process would complete very you can complete it easily. Notice that we could include a factor 2 times, okay. So 7 was there in case of 245 twice, okay. So we had to include 7 twice in our LCM as well, otherwise this LCM would not be divisible by 245, and that would of course be incorrect. Now let's move on. Let's first look at the summary of this process. What we did, we are including the factors which are common to at least 2 numbers, so that's what we did first. Then whatever factors were left in each of the numbers, we included those as well. So that was the process of completing the LCM, finding the LCM of a number. Very simple, okay. Again if multiple times the factor has to be included, we do that as well. Now with that, let us look at the properties of the LCM. See, it is the smallest number divisible by all the numbers. We understand that, okay. Just by the process, as we see, just by the process of finding the LCM, we have included the factors, the prime factors of each of the numbers in our LCM. So the LCM would have to be divisible by each of the numbers, by necessary. That is necessary because of the process, and by definition also. It is always greater than or equal to given numbers. So for example, if you consider these two numbers 6 and 12, the LCM of these numbers would be 12. This 12 is greater than or equal to, so this 12 is greater than 6 and it is equal to 12. So for this special case where the two numbers are multiples of each other, we have to put the equal to sign. So it is greater than or equal to given numbers. HCF in this case would have been 6. 6 was the highest common factor. Now if we are taking two coprime numbers, okay, of course by definition prime numbers are coprime. So for example, we took two coprime numbers 9 and 4. Our LCM is simply the product of these two coprime numbers. And why is that the case? Again, very simple, right? LCM has to include all the factors of 9 as well as 4. All the factors of 9 means 3 and 3. All the factors of 4 means 2 and 2. Since there are no common factors between 9 and 4, we have to ultimately include all the factors of 9 and include all the factors of 4, okay, because the two numbers are coprime, there are no common factors. So we had to include all the factors of 9, which is 3 into 3, and all the factors of 4, and this is nothing but 9 into 4, or just the product of the two coprime numbers. All the prime numbers are coprime, therefore the same applies to prime numbers as well. So for example, the LCM of 2 and 3 would simply be 2 into 3, which is 6. Okay, so this is LCM of 2 and 3, okay, note that. Now with that, we have covered all the properties, all the important properties of the LCM. Now let's see what kind of word problems are typical word problems, how are they structured for the case of LCM. So for the HCF, we already saw how the word problems were. For the case of LCM, the word problem typically go like this. Suppose we are given two scales, okay, so two scales or two measuring tapes. One of them, the length is 6, for the other, the length is 9. We will be asked to create the smallest wall which would be evenly divisible or evenly measurable by these two tapes. So that is how the typical problem of LCM would go. In the case of HCF, we had to create the scale, the largest possible length of the scale. So largest was the keyword there. Here, smallest, minimum, that is the keyword. Minimum possible length of the wall which is evenly measurable by these two tapes. So for example, if we take a wall of length 12 and we take the scale of length 6, we can possibly evenly measure it. Evenly measurement means that there is only fixed length, full lengths of scales would fit inside that wall. Of course, when I want to measure the same wall of length 12 using a scale of 9, I cannot, okay, because the scale of 9 would be covered only half, okay. I measure one full length of scale and then rest I will have to measure using half the using a part of the width of the scale, which is of course not allowed. We have to create the smallest length of the wall. This length should be such that it is evenly measurable by this one as well as this one. So 6 and 9, both the scales should be able to measure it, 6 centimeter as well as 9 centimeter completely evenly, okay. So 12 is not that number. So our number should be such that it is completely divisible by each of the 6 and 9. And what is that number? It should be smallest such number which is completely divisible by 6 and 9. And that number is of course the LCM. Now we know that. LCM of 6 and 9 is 18. We can find it out. And this would be the smallest wall which is evenly measurable by 6 as well as evenly measurable by 9. And that is by definition, because this LCM, this number 18, is the smallest number which is divisible by both 6 and 8. Right? So that is the 6 and 9. So that is by definition. Okay, so this 18 is divisible by both 6 and 9. So that is by definition, this 18 would be evenly measurable by both these scales. Okay, the key here is that smallest wall. It is the smallest such wall. So smallest, minimum, those are the keywords that we have to look for in a question. Lowest, smallest, minimum. Those are the keywords we have to look at in the question to find out that this is the word problem for LCM. Now let's take the example of such problem. We'll start with very simple problem. We have to find out the smallest 3-digit number which is exactly divisible by 6, 8 and 12. Most important thing here is that we have to find the smallest such number, but it has to be 3-digit. Let's just find out the smallest number first. We know that the smallest number divisible by all three of these numbers is simply the LCM of these three numbers. That is something we know. So LCM of 6, 8 and 12, we can find it out, and this comes out to be 24. So we'll use our method, the division method, and we'll find out the LCM of these three numbers, and it will come out to be 24. But that is not the trick here. 24 is not the 3-digit number. The key thing here, as we studied when we looked at the properties of multiples and LCM, at that time what we saw was that not only 24 but all the multiples of 24 are divisible by 6, 8 and 12. Okay, so if we consider all the multiples of 24, so the next multiple of 24 is 48. After that, 24 into 2 is 48. 24 into 3 is, if you look at the next multiple, it is 72. Then the next multiple comes out to be 96. And after that, the next multiple comes out to be 120. So these are all the multiples of 24. So 24 is of course the LCM. So that is the lowest possible number which is divisible by 6, 8 and 12. But we are not being asked the lowest possible number. We are being asked the smallest possible 3-digit number. So we have to continue with this multiples of 24, ultimately reaching the 3-digit number. So all of these numbers, all of these multiples of 24 would also be divisible by 6, 8 and 12. And note that these are the only numbers, all the multiples of 24 are the only numbers which would be divisible by all of these three. So we don't stop at 24, the LCM. We find out the multiple of 24, the smallest multiple of 24, which is the 3-digit number, and that comes out to be 120. So 120 would be answered here. Okay, keyword is 3-digit number. Okay, we are not only looking for the smallest number but the smallest 3-digit number. So problem is of course of LCM, but we have to do a little more work. The next problem is that we have to find out the least number which when divided by 6, 15 and 18. Okay, so it does not evenly divide these numbers. It is not evenly divided by these numbers. Number which is completely divisible by 6, 15 and 18 is of course the LCM. We know that. So let's just find out the LCM of 6, 15 and 18. Okay, so that part is simple. We can quickly find that out, and that number is 90. So that part is simple. That is the LCM of these three numbers. But we are not being asked for a number which is divisible by all three. If that was the case, 90 would have been answered. But we have to find the number which leaves a remainder of 5 when divided by each of these numbers. So think about this a little. 90 when divided by each of these numbers, 6, 15 and 18, what is the remainder that 90 would leave? Of course, because it is evenly divisible, the remainder would be 0. What about if we divide this 90? What about instead of 90, we did 90 plus 1 and we divided it by 6. So in that case, you would say that 90 is completely divisible. So till 90, we would just compute the division would be complete. But this 1 would be left extra, okay, for each of these numbers, and that 1 would be the remainder. What about 92? 92 when divided by, let's say, 15. So 15 6 are 90, but 2 would be left as remainder. So when 92 would be divided by each of these numbers, then my remainder would be 2. So to get the remainder of 5, what do I have to do? My number would be simply the LCM, which is completely divisible by these numbers, plus I have to add 5 to it. So this extra 5 would be reflected in the remainder as well. So this number comes out to be 95, and 95 is divided by each of these numbers. This 5 which we added to the LCM just reflects as the remainder. So that is again the key trick in this question. Now let's move on to the very next question. This is similar to what we saw in case of scale. There are 3 boys and their step length. Okay, so again in this case we are looking at the step length. So it is 63. For the second boy, the step length is 70, and for the third person, the step length is, let's just write it down as 77. So instead of scale or tape, we are using the step length, but still the problem is the same. We have to find out the distance they have to cover, the smallest possible distance that they need to cover, so that they have taken an even number of steps. Okay, they have taken no half steps. Okay, only full, they can cover this distance in full steps. So how do we do that? The distance, whatever this is, has to be divisible by each of these numbers. And what is that number? That is of course the LCM. So our answer in this case is simply the LCM of 60, 70 and 77. And of course, you can calculate this using the long division method. Okay, that is the preferred method. Let's just do it just once for one question so that you get an idea of how to go about doing it. 60, 70 and then 77. Okay, so 63, 70 and 77, we write this down, and the first number that we divide is of course 7. So this comes out to be 7 9 is 63, then 10 and then 11. Now since 11 is, there is no common factor between 11, 9 and 10. Okay, so even with 2 pairs of number I cannot find any common factors. So therefore I stop the process right here. So the LCM just comes out to be 7 into 9 into 10 into 11, which of course comes out to be 6930. So you can compute it, and this 6930, this distance of 6930 is evenly divisible by each of this step length, which means that they would take a fixed number of complete steps to cover. Each of them will take complete steps to cover this distance. So again, very simple, not difficult at all, provided we are solving the problems systematically. Let's just quickly understand the difference in calculating LCM and HCF, because a lot of the students are actually confused here. So we are just clarifying it a little bit again, just to make sure that there is no confusion whatsoever. So let's just try to find out the HCF of these 3 numbers first. Okay, so we'll first find out the HCF. The key to finding out the HCF is that we have to make sure that the number that we write here is such that it divides each of these numbers. Okay, unless it divides all of these numbers, we will not write it here, we will not do the division. Okay, so it has to divide 12 and all of them. Okay, so it has to divide 12, so get answer of 4, and then it has to divide 18 and we get answer of 6, and it has to divide 27 and we get an answer of 9. Okay, so 3 would be that number. After that, between 4, 6 and 9, we are not able to find any other common factors. Okay, so between these 3 numbers, all of 3 of them taken together, okay, we are not taking 2 of them, we are not taking any one of them, we are taking them all together. There is no common factor. 2 is common factor of only these 2, 3 is common factor of only these 3, only these 2, only 6 and 9. So we will not use those numbers at all, and we will say that the HCF is simply 3. We'll just stop here. Okay, Key being that a number is written here, the division is done only when it divides each of the numbers here. Okay. For LCM, the first step is the same. Okay, so we divide using the 3. So we get 4, 6 and 9. After that also the division continues as long as we are able to find a factor which is common to at least 2 numbers. So now we will use 2 because it is common to these 2 numbers, and we'll continue the division, and of course the 9 would come as is because this cannot be divided, and then we'll use 3 again because 3 is common to at least these 2 numbers. So 2 would come as such, and then 3 ones are 3, 3 threes are 9. So our LCM then becomes 3, 3, 2, 2 and 3. Okay, so this becomes 3 into 2 into 3. So we went like this, and then into 2 into 3. So the key difference was that we continued the division afterwards in case of LCM, but not in the case of HCF. So note that difference, and the answer, if you were to compute it, this would come out to be 108. Okay, so very important thing, don't get confused between calculation of LCM and HCF. Students do get confused, so keep this concept clear in your heads. Very important. Now let's look at a very important topic, which is prime and composite numbers. So before we start looking at prime and composite number, let's just understand what it really means. So here we have number 6. We have seen that we can represent it as a number of factor trees. The first 2 factor trees, the first and the last factor tree, are not so interesting because number 6 appear as factor of itself, which of course would continue forever. The other 2 factor trees are very interesting, and here we have replicated that. What we have essentially done in these factor trees is that we have broken number 6 into 2 of its constituents, 2 and 3. We are able to break 6 into its factors other than 1 and 6 itself. Okay, so that's what we have done here. Same in the other case. We were able to break 6 into 2 factors other than 1 and 6. This is not true. So we were able to do it for 6. But let's try to do it for number 3. Can we break number 3 and number 5 into 2 factors other than 1 and 3 and 1 and 5 itself, right? So can we do it for 3? Can you find 2 factors other than 1 and 3 itself, and for in case of 5 other than 1 and 5 itself? Can you find 2 factors? We have tried to hammer them, we have tried to run bulldozer over them, but these 2 numbers 3 and 5, they will not break into smaller factors. Only 2 factors of number 3 and 5 are 1 and the number itself. Such numbers are known as prime numbers. Very important. They have exactly 2 factors. They don't have 1 factor, they don't have 3 factors. They have exactly 2 factors, which is the number 1, the 1 and the number itself. Those are the only 2 factors of such numbers 3 and 5, and they are known as prime numbers. Let's look at number 1. Let's try to divide it into 2 factors. The only possible factorization for number 1 is 1 into 1, which means that it has a single factor. It has 1 factor, which is number 1 itself. And because it only has 1 factor, which is 1, therefore it does not have 2 factors. I cannot divide 1 into 2 factors, and it is not a prime number. So 1 is not prime because it has a single factor, which is the number 1 itself. Now, on the other hand, we have numbers such as 6, which can be divided into 2 smaller numbers, which can be expressed as product of 2 numbers other than 1 and the number itself. So for example, 6 can be written as 2 into 3. Of course, 6 can also be written as 6 into 1, but this is not so interesting for us. The more important thing is we were able to express 6 as product of 2 numbers other than 1 and 6 itself, and because of this 6 is not a prime number. Such numbers are called composite numbers. They have more than 2 factors. So in case of 6, we not only have 6 and 1 as factors, but we also have
2 and 3 as factors, and therefore 6 is known as composite number. It cannot be prime because it has more than 2 factors. It does not have exactly 2 factors, so therefore it is not prime. It is known as composite. Let's look at our number 1 again. 1, as we said, can be expressed as 1 into 1, which means that 1 has a single factor, which is number 1. Because it does not have more than 2 factors, 1 is not a composite number either. This is very important. 1 is a special number. It is neither prime nor composite. It is not a prime because prime numbers have to have exactly 2 factors and 1 only has 1 factor. It is not a composite because composite numbers have to have more than 2 factors, and again 1 has only a single factor. It is neither prime nor composite. So remember this fact. It is very, very important. Now with that, let's move on to a game. Let's play a game. See, here we have a lady playing against a robot, and of course this lady is very, very intelligent because she is a subscriber of Examrace channel. So the game goes like this. Our lady picks up a card from this set of 50 cards. Let's say that she picks up 6. Her opponent, in this case Mr. Robot, would then get all the factors of 6 for free. So we know that factors of 6 are 1, 2 and 3. So the opponent, Mr. Robot, he would get all the factors of 6 for free. This he gets for free. And he is also allowed to pick one more card from here. In the end, the person whose sum of the cards is highest actually wins. So Mr. Robot now thinks that, with his twisted mind of course, he thinks that to get highest total in my cards, let me pick the largest card. So he picks up the number 50. That's what he does. Now of course, as soon as he picks up the largest number 50, our lady, she gets all the factors of 50, which is 25, 5 and 10. So 50 is divisible by all these numbers, 5, 10 and 25. So she gets all of these cards. And at the same time, she realizes that the strategy of picking the largest card is not really working because I am getting even large number of factors from these larger cards. So then she thinks, how do I solve this problem? Which card from among here I should pick so that my opponent would not get any factors? What are those numbers which have minimum number of factors? My friends, those are our friends, prime numbers. Prime numbers are our friends here. So she is smart, she is intelligent. She chooses a prime number. She decides to choose a prime number so that her opponent would not get any factors. Prime numbers don't have factors, only factors are 1 and the number itself. So our opponent would not be able to get any factors for free. Now which prime number she should choose? Now that's a difficult problem. Ideally, she would have to choose the largest prime number because if she does that, her card total increases the most without benefiting her opponent. So she is smart of course, and she has studied this class in detail. So she knows that the largest prime number in this case is 47. She picks it up, and now because of our opponent, he does not get any factors for free, is really confused, and lady, she is of course winning. If she continues this strategy, she would continue to win. See, one more thing that a person picking the card can do is that it is okay in this case to pick a number, a composite number as well, as long as none of its factors are present on the board. So if all the factors have been removed, then I can pick a composite number as well. Now let's see how we can find out the prime factors, right? So for winning this game, prime numbers. So for winning this game, we definitely need all the prime numbers. We need to find out all the prime numbers that we can, and how do we find them? So let's understand that. But before we do this, let's just understand two very, very simple concepts. The first concept is all the multiples of prime numbers are composite numbers, which is correct only, right? Let's take any two prime numbers, 2 and 3, okay? Or let's take two prime numbers, 2 and 2. If I write down their multiples, for example 6 and for example 4, right, 6 and 4, then because 6 would have factors in addition to 1 and 6, right, because they were formed, 6 was formed by multiplication of two prime numbers, so definitely it would have factors other than 1 and 6, and it would definitely be a composite. Similarly, 4 was formed by multiplication of two prime numbers, 2 and 2. Therefore, it would definitely have, in addition to 1 and 4, it would definitely have the factor as 2, and it would also end up being composite. So all the multiples of prime numbers, so all the numbers which appear in table of prime numbers would be composite numbers. Very, very important. Second important property is that all the composite numbers can be expressed as product of prime. So this we have already seen, right? In the factor tree, we were able to express, for example, number 12, if we draw the factor tree, then we are able to express 12 as a multiple of its prime numbers, as a product of its prime numbers. So we can do that, definitely we know. With this understanding in our mind, let's move on to the very, very important topic. Now, finding out prime numbers is of course a very important task, and the first such effort in this direction was actually made by a Greek mathematician, Eratosthenes. Now, Eratosthenes was not really only a mathematician, he was a very intelligent scientist, and he was the first one to find out the circumference of the earth. He was also the first person to actually find out the tilt of the earth. So he was a very important contributor to several fields, and his sieve method was the first systematic way of finding out the prime numbers. So the method, we look at how it works by considering all the numbers from 1 to 100. Right at the beginning of this method, what we do is that we mark 1 as not being a prime number, because 1 is not neither a composite nor a prime, we know that. So we cancel out 1, we do not bring it into consideration at all. The method works by actually removing or filtering out all the composite numbers. So whatever numbers are really left behind would naturally be prime numbers. So that is the basic idea of this method, and we systematically go from one number to the next, marking out all the composite numbers in the process. So let's start. So the next number after 1 we consider is number 2. What we do is that we find out all the multiples of this number 2 in this list, and we say and we cross them out. See, all the multiples of number 2, for example number 4, in addition to having 1 and 4 as factors, this number 4 would also have 2 as factor, and therefore it can never be a prime number. The same is true for other multiples of 2 as well, and therefore we cancel out the other multiples of 2. So all we just say the table of 2 and we cancel the numbers out, or we look at all the even numbers which have definitely would have 2 as a factor and we cancel them out. Either way, we have cancelled quite a few of these numbers and removed them as our candidates from being the prime number. So now these are the numbers, these are the possible candidates for being the prime numbers, and the candidates are shown in pink according to our convention. The numbers which have been grayed out cannot be prime numbers, so we have already removed those from our consideration. They are the non-prime numbers or the composite numbers. Next, we move on to number 3. Now at this point, I would like you to consider this. When we reach a number, we have already looked at all the numbers below it. So when we reach 3, we have looked at number 1, we have looked at number 2 already, right? So we have looked at number 2 already when we reach 3. Similarly, when we reach other number, we have looked at all the numbers below it, and we were not able to find a factor of number 3 in those numbers. So when we looked at all the numbers below 3, in this case only there is only one number 2, and we were not able to find a factor of number 3 below number 3. Otherwise 3 would have been cancelled. So 3 is not cancelled, which means that 3 has only 2 factors, 1 and 3 itself. This means that when we reach a number and it has not been cancelled, it has to be a prime number. We were not able to find any factor of that number below that number. So the only possible factors are 1 and the number itself, and it has to be a prime number. So now we mark 3 as a prime number. So in our case, we are marking the prime numbers as blue. So we do that, and we then consider all the multiples of number 3. So the first multiple of number 3 is 6, which is already cancelled out, so we don't have to worry about it at all. Next multiple of 3 we consider is 9, and we gray it out. So we are graying out all the multiples of number 3 now, and of course we gray them out and we remove all the multiples of number 9 because they have to be composite numbers. In addition to having themselves and 1 as factor, they also have 3 as factor, and they can never be a prime numbers. So all of those 9, 15, all of those are now gone. Now at this point, let's move on to the next number and consider number 4. See, the thing about number 4 is it is already grayed out. So we know that it can never be a prime number. It is definitely a composite number, which we already know, right? Because 4 has 2 as a factor. So therefore 4 is definitely a composite number. It is not a prime number. So that much we know. What about multiples of 4? Do we have to consider the multiples of 4 at all? See, we don't have to consider multiple of 4 at all because they would have been cancelled already by virtue of the factors of 4. Okay, so when we consider the factors of 4, we would have cancelled the multiples of 4 as well. For example, let's consider multiple of 4, which is 8. So this 8, when we consider a factor of 4, that is 2, we not only cancelled 4, but at the same time we cancelled 8 as well. So in that, what does that mean? It means that when we come to a number and it is grayed out, we can completely ignore that number. That number can never be a prime number, and we don't have to consider the multiple of that number at all. So we ignore 4 completely. We don't do any maths with it, and we move on to the next number, which is number 5. Of course, 5 has not been cancelled so far, so we mark it as prime. The only possible factors of 5 are 1 and 5 itself. We are not able to find any factor below 5. So 5 is marked as a prime number, and then we go on to mark the multiples of 5 as composite numbers. So all the multiples of 5 of course appear below 5 as such, and they are marked as composite numbers and removed from our consideration completely. Next we move on to number 7, and we do the same process. We mark 7 as a prime number because it has not been cancelled yet, and after that we mark all the multiples of 7 which have been left so far. We remove it from our consideration and we gray them out. Now you have to understand that we did not look at 6 at all because all the multiples of 6 have already been cancelled when we looked at either 2 or 3. So 2 or 3 are factors of 6, and when we looked at 2 or 3, we would have cancelled all the multiples of 6 as well. That is the first thing to note at this point. The second thing to note at this point is that we do not have to go above number 10 when doing this process. Why is that the case? See, let's consider the number 11 for example, and let's understand why we don't have to do this process for number 11. The only way I can come up with multiples of 11 in this region from 1 to 100 is by multiplying number 11 with numbers from 1 to 9. Okay, so only when I multiply number 11 with numbers from 1 to 9, I can get a number which is less than 100. 11 9s are 99. If I go above 9 and I say 11 into 10, then I get a number which is above 100. So at this point, I know that when I am considering number 11, okay, I have already considered all the other factors with which 11 could be multiplied to get a number below 100. So because I have already considered and I have already cancelled all the factors of numbers from 1 to 9, I don't really have to consider the multiples of 11 at all, because those would have already been cancelled when I looked at the numbers from 1 to 9. This means that I only have to go till number 10. Repeat this process. In this sieve method, I only have to go till number 10. The speciality of number 10 is that it is square root of 100. So 100 is our last number, and I only have to do this process until I reach the square root of 100, which is 10. Numbers above 10. For numbers above 10, we would have already cancelled those numbers when we looked at the other factor of that number, which would have to be below 10 in this case. So that completes the sieve method, and these are all the factors. The pink numbers which are left here and the blue numbers which are left here are now our prime numbers. Right? So we'll mark the prime numbers blue to complete our process, to complete this convention, and this is what we get. At this point, let's now understand some special primes. So we have looked at all the prime numbers from 1 to 100. There are certain primes which are very special here. So the first such concept is that of twin primes. So what are twin primes? Twin primes are two primes which differ by 2. So the difference between those two primes is 2. Of course, 2 and 3 are not twin primes. Why is that the case? Because the difference between 2 and 3 is 1. In case of twin primes, the difference has to be 2. So here are some examples. 3, 5, 5, 7, 7, 19. They are all twin primes. The difference between these two primes is actually 2. 2 itself is a prime number, and it is a very special prime number. Why is that? Because 2 is the only even prime. All other even numbers have 2 as an additional factor, and therefore they cannot be prime numbers. So 2 is not only the smallest prime, it is also the only even prime, and therefore 2 is in itself special. But 1 and 2, they are not twin primes. Twin primes have to have a difference of 2 between them. The next important concept is that of prime triplets. Prime triplets are 3 primes which have 6 as difference. For example, let's look at some prime triplets. 5, 7, 11 are actually prime triplets. Difference between 5 and 11 is actually 6. Similarly, difference between 7 and 13, in case of 7, 11, 13 is actually 6. So these are twin primes. Prime triplets. Prime triplets are always of 2 forms. So we said that they would be P and then a number in between and then 6P. That is the form of prime triplets. The other thing, 6 plus P, that is the form of prime triplets, because this number, the last number, the highest number, has to be 6 more than the first number on the minimum numbers. The number between in here can take 2 forms. Either it is of the form of 2 plus P, or it is of the form of 4 plus P. So those are the only 2 forms of prime triplets. So that is the case of prime triplets. Another interesting thing to note about twin primes, okay, which I forgot earlier. So now we are talking about twin primes. Remember that the sum of the twin primes, except the first one, 5 and 8, their sum is always divisible by 6. So that's another important thing. Okay. For twin primes, their sum is divisible by 6 except for the first twin prime, except the first pair. And in the case of prime triplets, their difference is always 6. So that is something to note here. Now, with that, let's just look at how we can find whether a number is prime or not. Okay, so we looked at the sieve of Eratosthenes, and we saw that, of course, one of the method is to do this process of sieve method and to find out whether the numbers are prime or not. So that is, of course, one of the methods. The second method would be brute force method. For example, if I am been given a number, let's say 97, and I want to find out whether it is prime or not, what I can do is that I can continuously divide it by various numbers, 2, 3, 5, 7, various prime numbers until I reach the root of 97. Okay, so that's where I need to stop. I can stop at root of 97. So that process is actually simple, because root of 97 would be less than 10, so we are fine. Okay, we'll only have to go till 9. So for these smaller numbers, this process does not look too cumbersome. Okay, it doesn't look too bad. What about larger numbers? Say if I asked you to find out whether number 583 or whether number 199 is actually prime or not. In that case, we have to go quite a ways to figure out whether number is prime or not. For in the case of 199, I have to go till 15 around root of 199. In case of 583, I have to go around till root of 583 around 24. So those are the numbers till which I have to try to divide number 583 to really figure out whether 583 is prime or not. So this process quickly becomes very, very cumbersome. So finding out whether a number is prime or not is a very difficult task. It's computationally expensive. If I take two prime numbers, so in this case 583, that's exactly what I have done. I have taken two large prime numbers, relatively large prime numbers, 11 and 53, and I have multiplied them together to get 583. So if that is the case, if I take two very large prime numbers and I multiply them together, then it is very hard for me to find out whether their product is actually prime, first of all. Second, to do a prime factorization of their product. So to do prime factorization of a number which is made by two very large prime numbers is a computationally difficult task. And this fact is used in cryptography, extensively used whenever you are sending your password, your email to any server. This is the process which is used there. They are somehow using product of two very large prime numbers to secure your data. Very interesting, isn't it? In order to do the prime factorization and to find out if a number is prime or not, we need to look at the divisibility test. So very, very important, these divisibility tests, because we are not computers after all. So we need to use the aid of this divisibility test to quickly do factorization and to quickly find out if a number is prime or not. So here are the first kinds of divisibility tests. Here we just simply can find out if a number is divisible by let's say 2 by looking at the last digits, just by looking at the last digit. A number is divisible by 2 only if the number is even. That is very, very simple. Okay, so numbers like 2, 4, 6, 8, they are even numbers, and those numbers are divisible by 2. If you look at their last digits, they definitely follow a pattern. Okay, so then next will come 12, 14 and 16, 18 and 20. Okay, so these are the last digits of our even numbers. Okay, they are 2, 4, 6, 8 and 0. So only in that case we would find those numbers to be divisible by 2. What about divisibility by 5? Numbers are divisible by 5 if they either end in 5 or 0. Only in that case are they divisible by 5. Very, very simple. Normal circumstances, if you look at the table of 5, those are the only two kinds of numbers that you would actually find. Divisibility by 10 is also very, very simple. If you look at the table of 10, the only numbers you will find there are the numbers which end in 0. So those are the only numbers which are divisible by 10. Divisibility by 100 is also very simple. Numbers would have to end in 2 zeros. So I would need 2 zeros for 100. Okay. So those are the divisibility tests, simplest ones, where we just need to look at the digits of a number. The next kinds of divisibility tests are those where we have to do the sum of the digits. So here we have to do sum of the digits. For example, let us look at a very, very simple number. Sorry, not such a simple number, but very, very simple divisibility test. So here we have a number 61809, and the sum of the digits of this number, okay, if I add all the digits, that sum comes out to be 24. Now because this 24 is divisible by 3,
the number itself is actually divisible by 3. So if the sum of digits is divisible by 3, the number is divisible by 3. If the sum of the digits is divisible by 9, the number is actually divisible by 9. Again, let's look at a simple example. Let's look at a very simple example. Let's see 54. What happens? 5 plus 4 is 9. And of course, we know that 54 is divisible by 9 and 9 is also divisible by 9. So the sum of the digits is divisible by 9. The number itself is divisible by 9. So those are the very simple rule for divisibility test of 3 and 9. Let's try to get an intuition for why they actually work. So here, what I'll do is that I'll write a number, a 4-digit number as A, B, C, D. Okay. This I can write in expanded form as, and we have all studied expanded form already. So in our earlier classes, I can write this as in this way. Very, very simple, not difficult. Now what I do is that I break this 1000 using the distributive property. Okay, using the distributive property, I can write down this 1000A as 999A plus A. I can write this 100B as 99B plus B. This 10C, I will write it as 9C plus C, and this D would come as such. So here I have done nothing. I have just used the distributive law as such. Then I combine these terms, 99A, 99B, 9C. These things I can combine. And one of the things that you will immediately notice as soon as you write it is these terms all have factors of 9. Okay, so I can simply write it as, I can take out the, I'll use the inverse of distributive law, and I will write it as, the inside thing I will write it as 111A plus 11B plus C. And no matter what this thing is, it doesn't matter. All of this would always be divisible by 9. So this entire term, all things are always divisible by 9 as well as 3, because 9 is a factor of this term. So this entire term is divisible by 3. Of course, we left these 3 numbers, these 4 numbers. So we have to write them down as well. So here we'll write them down. A plus B plus C plus D. So, and there is of course an addition sign between these two. So these 3 terms are here, and these 4 terms A, B, C and D, they are here. This term is always divisible by 9. So my remainder cannot come. If I divide by 9 or 3, my remainder cannot come from here. My remainder always has to come from here. If this thing, the sum of the digits, this is essentially what? Sum of the digits. If the sum of the digits also becomes divisible by 3 or 9, the entire number would become divisible by 9, because this thing is always divisible. If I make this thing also divisible by 3 and 9, the entire number becomes divisible by 9. Okay, so that is the intuition behind behind this property of numbers, behind this divisibility test of 3 and 9. Similarly, we have a property of with divisibility test of 11 as well. So here for 11 we say that if I sum the odd digits and I make a difference of odd digits, sum of odd digits and a sum of even digits, that number, if it's 0 or divisible by 11, the entire number is divisible by 11. So here let's just use an example to find this out. Okay, so let's take an example of 627. Here we'll first use the odd digits. So odd digits, so let's just write down the numbers of, what are the numbers of the digits. This is first digit, second digit, third digit. So these are the odd digits, first and third. So I make their sum, and then I do the difference with the even digit, which is just 2 in this case. If there was other even digits, I would sum all of them together. This comes out to be 7, 8, 9, 10, 11, 12, 13. This is 13 minus 2, and this comes out to be 11. And 11 is of course divisible by 11. And therefore my original number 627 is also divisible by 11. The same exercise, let's now do it for 4 digits and see how we would do this. We can do 3, 1, 3, 5. Okay, so that is the example we'll take next. Again, we'll number the digits 1, 2, 3 and 4. We'll sum these digits 5 plus
1, those are the odd digits, and then we also sum the even digits, that is 3 plus 3, and I subtract 3 plus 3, okay, and I subtract those two together. Okay, these two sums I subtract with each other, and the answer comes out to be 0. If the difference between them is 0, we already said that the number is divisible by 11. Therefore, this number is also divisible by 11, and you can test it. Indeed, it is divisible by 11. Why does this property work? So let's get some intuition as we did in the earlier case. Again, we'll write down the digit sets a plus abcd, and this is nothing but, we'll write it in expanded form, 100b plus 10c plus d. Again, we'll use trick and we'll just write these digits a little differently. So d, we cannot do anything with it, so d will keep as such. This number 10c, what we'll do is that we'll just write it as 11c minus c. So that's what we'll do. We can do that, okay. So I've created a multiple of 11, if you notice. Then this 100b, we'll simply write it as 99b plus b. I can do that, and of course there is an addition sign right here. This 1000a, we can simply write it as 1001a minus a, and of course there is a addition sign right here. Now again, I combine these terms. What do I get? A plus 99b plus 11c, and these terms, if you were to check it out yourself, they are all divisible by 11. So this entire thing is actually divisible by 11. So this divides by 11 completely, evenly. If any remainder were to be there, it has to come from these, and of course minus a, which is nothing but, if I were to write it in a nice way, this is nothing but, I lose b plus d minus a and minus c, I'll combine, and this becomes a plus c. Okay, so this is nothing but our sum of odd digits minus the sum of even digits. So if this sum of odd digits minus sum of even digits also happens to be a multiple of 11, okay, if this was also divisible by 11, this entire thing would become divisible by 11. So this is how this divisibility check works out. This is always divisible by 11. So all I need to check is whether this is divisible by 11 or not, and that is what I am doing. That is my divisibility test. So okay, hope you got the intuition behind these divisibility tests, because it will help you remember them in a better way. Now we move on to simpler tests. For in case of 4, my divisibility tests are very simple. If the last two digits are divisible by 4, my entire number becomes divisible by 4. So let's take an example, 136. If I divide it by 4, I know that 36 is divisible by 4. Therefore, this 136 also has to be divisible by 4, and that is indeed the case. This answer comes out to be 34. Okay, so if I were to find the answer, I can find it out. Let's just take another example. This time we'll use the example of last 3 digits. Okay, we'll try to find out the divisibility test for 8. In case of 8, if the last 3 digits are divisible by 8, my entire number is divisible by 8. So I need to check the last 3 digits. In this case, the last 3 digits are indeed divisible by 8. 136 divided by 8 is equal to 17. So this 136 is divisible by 8 completely. Therefore, this entire number 1136 is also has to be divisible by 8, and my answer in this case is 142. So for 8, check the last 3 digits. For 4, check the last 2 digits. Okay, last 3, last 2. Very simple. Now let's see how we can combine the various divisibility tests together to use it to our advantage to extend the utility of those divisibility tests. So here is the first rule. If we can find a number which is divisible by 2 coprime numbers, then it is also divisible by their product. So what does that mean? It means that let's take a number, let's say 72. Okay, we say that 72 is divisible by 4 and 72 is also divisible by 9. Since 4 and 9, they are coprime, they don't have any common factors between them. Therefore, this 72 would also be divisible
by the product of these two coprime numbers, which is 9 4s are 36, and it is of course divisible by 36. The answer comes out to be 2. So that is what this rule says. Again, we have extended the utility of our divisibility test, and we are able to create the divisibility test of 36 by using the divisibility tests of 4 and 9. Okay, that is what we have done actually here. The second rule states just that. Okay, a number is divisible by a given divisor. Let's say 36 again. So 72 would be divisible by 36 if it is divisible by highest power of its prime factors. So what are the prime factors of 36? It is 2 into 2 into 3 into 3. Now if I combine these prime factors together, for example, I combine 2 and 2, I combine 3 and 3, so I can write it as highest power of the prime factor 2 is 2 square, highest power of prime factor 3 is 3 square. So what this rule is saying is that if our number 72 is divisible by the highest power of the prime factor 2, which is 2 square, and it is divisible by the highest power of this prime factor 3, which is 3 square, then the number would also be divisible by 36. Okay, so 36, the highest power is of 2 is 2 and highest power of 3 is 3. Ultimately, we have done the same thing. We have created the two numbers. We have divided 36 into two numbers which are both coprime. So this is 4 and 9. So we were able to divide 36 into two coprime numbers, 4 and 9. And if 72 is divisible by 4 and 9 individually, then it would also be divisible by the product of those two coprime numbers. 9 4s are 36. Okay. See, to create a divisibility test of 36, we have to divide 36 into two coprime numbers, and that is the most important thing here. I can create a divisibility test of 36 by dividing it into two numbers 4 and 9, which are both coprime. If I were to divide 36 in, for example, 12 into 3, and then I check the divisibility by 12 and 3, I cannot say anything about divisibility by 36. So this would be completely wrong. To create a divisibility test of 36, I have to divide it into two coprime numbers. That is the most important thing. Okay, and it will of course extend the utility of our divisibility test. The next important rule is that if a number is divisible by a given number, for example, let's say that 24 is divisible by 6, then 24 would also be divisible by each of the factors of 6. Okay, so if 24 would be divisible by 2, it would also be divisible by 3. That is what this rule is saying. Each of the factors of number 6. Okay, here we are not constrained by just the coprime factors or factors which are coprime. We are just saying that if 24 is divisible by 6, it will be divisible by all its factors, no matter whether we have divided 6 using coprime numbers or not. Okay, so that is what this rule is saying. The next rule is, if I have two numbers, let's say 12 and 20, and this 12 and 20, they are both divisible by 4, then there's sum and difference. So if I do 20 plus 12 or if I do 20 minus 12, both of these would also be divisible by 4. This is what this rule is saying. And of course we know that 20 plus 12 is 32, which is divisible by 4, and 20 minus 12 is 8, which is also divisible by 4. And this to some extent comes because of the distributive property, because I can write 20 as 4 into 5, and then there is a plus or minus sign here depending upon what we choose, and then 12 can be written as 3 into 4. Now if you notice, 4 can be taken out common, and what we are left with is 4 into 5 plus minus 3, and of course this part is always an integer, and 4 has been taken out common, so this entire thing would be divisible by 4. This entire number is divisible by 4, which means that 20 plus 12 and 20 minus 12 would be divisible by 4. So we have used somewhat inverse of distributive law here to just prove this fact. Okay, so very simple. These divisibility tests are very important, and with these rules, the combination rules, you can use them for bigger numbers as well. By using the smaller divisibility test can be applied to bigger numbers. you have the divisibility test of 11 and 4. You can apply it to, for example, 44 by using these simple rules. And of course, divisibility tests are useful. They are useful when we want to find out if a number is prime, and more importantly, they are useful when we are doing the prime factorization of numbers. So definitely use this divisibility test. They would help you solve the problems quickly. Okay, because ultimately that's what we have to do. We have to not only solve the problem, but we should do it in a given time, and your teachers are expecting you to use the divisibility test when creating such problems. Now with this, we covered this chapter completely. Very, very important chapter of arithmetic, of course, but the things do not really end here. There are certain advanced topics which students who wish to give Olympiad, other exams, important exams, need to actually cover. And don't worry, some of these topics are already covered on our channel, so look at those videos. Other topics we would be covering shortly, so stay subscribed. Thank you.